Hey guys, so today we're doing another Euler's method example, so let's just look at what we have here. Okay, consider the initial value problem. Y prime equals sine pi t and y of 0 equals 0. Use Euler's method with 5 steps to approximate y of 1. Let's write out what we know. So we know let's use orange. So we know our derivative function is y prime equals sine pi t. We know y of 0 equals 0, which is our initial point. And we know that we have to use 5 steps to approximate y of 1. So we're looking for y of 1, but we need to use 5 steps to do that. So how do we do that? Okay, so if we're going from 0 to 1, let's make a number line. If we're going from 0 to 1 and we need 5 steps to go to 1 from 0, we need to have an interval to do that. So how to find 5 equal intervals from 0 to 1, you just divide 1 by 5 and you get 1 by 5 is 0.2. So our interval will be 0.2, and remember from my last videos, our interval is represented by delta t or delta x, whatever case is in the problem. So here we have delta t equals 0.2 because 5 intervals from 0 to 1 is 0.2 each. So we'll have 0.2, and then our second interval will be, our second step will be 0.4, our third step will be 0.6, and our fourth step will be 0.8, and our fifth step will be 1. So that will bring us the approximations that we need. And the way we'll do that is we'll have to approximate y of 0.2, y of 0.4, y of 0.6, y of 0.8, and y of 1. So we'll just approximate all of those, and we'll just use the outcomes of each to get what we need until we get to y of 1. Actually, one more thing to point out. So like I said in my last video, if you haven't seen it, I'm just going to go over this really quickly. These intervals are represented by n. So this would be n1, n2, n3, n4, and n5. And respectively, this t value would be t1, t2, t3, t4, and t5, just to make things a little more clear. Okay, so now let's do the math. Let's write out our Euler's method equation in general terms, so not in function notation. So that would be y sub n plus 1 equals y sub n plus the slope of the point at x sub n and y sub n times the delta x. This is just the general, so instead of delta x, in our case we'll be using t's, so it'll be delta t. So let's begin. So what is the first approximation we need to do? We need to do this one, the first one, n sub 1 and t sub 1, so that would be 0.2. So we'll be starting with y of 0.2. Just write this out. So y of 0.2 approximates to, according to our Euler's method equation, what we plug in first is the y value of the initial point, which is 0, 0, because that is our initial point. So the y value of this is 0, so we just plug in 0 here, plus the slope of that point, which is, we'll just do it on the side. So the slope is, you find the slope through the derivative function, which is sine pi t. So we just plug in that point. So on the side, y prime of, what was our point, 0, 0, equals sine pi of 0. And we're only plugging in the t value, not the y value, because the derivative function only calls for a t value, not a y value. So we don't need to worry about that. So we plug our slope in, which is sine of 0, and we multiply this according to our Euler's method equation. We multiply this by our interval, which is 0.2. So this turns out to be 0 plus sine of 0 is 0 times 0.2 is 0. So this is just 0. 0. So our point turns out to be 0.20. So we're not done yet. We still have a couple more steps to go, but that's just the fun of Euler's method. So the next step will be y of 0.4, because our interval is going up 0.2. So we add 0.2 to this to the previous 0.2, and we get 0.4. Approximates to the y value of the previous point, which is 0. So we just plug in a 0 here, plus the slope of the previous point. So we'll just plug that into this, and we'll get. So we're only plugging the 0.2. If you can see that, we're only plugging the 0.2 because it is a t value, and that's the only thing that matters in this problem. So we'll plug that in. That's our slope. I'll write it as 0.2 pi times our interval 0.2. 0.2, yeah. So I'll just use a calculator to do this because we need it. So 0 plus sine 0.2 pi times 0.2 is this number, 0.11755, blah, blah, blah. So for this problem, we don't want to round the problems as we go. So you want to plug in this actual number when you're plugging in these values for the consecutive steps that we're going to do. Because if you round it, you'll get an answer that is not exactly right, and you want the right answer. So I'm just going to write 0.117 ... So next step, we will be doing the y of 0.6 because it's the next step. So let's go ahead and do that. Y of 0.6 approximates to the y value of the previous function, which was the big old 0.117 blah blah blah. So we'll plug that in, blah blah blah, plus the slope of the previous point, and our previous point was, I should have written that down, 0.117, not 0, I'm sorry, it'd be 0.4, because our t value here is 0.4, yeah, so it'll be 0.4 and 0.117. So to find the slope of that point, just do that at 0.4117, 0.117, blah, blah, blah. And we're all using our t value again because it only calls for that. So sine times 0.4 pi, and we plug that in, times our delta t, which is 0.2. And let's plug that into the calculator. So I'm just gonna hit plus right here so I get the entire number, and I'm gonna add sine 0.4 pi times 0.2. And we get 0.3077 blah blah blah. So we'll do the same thing that we did before and do that. So the next one is y of 0.8 because we're adding a 0.2 interval to this. So we get y of 0.8 approximates to the y value of the previous equation, which is this value right here, plus the slope of the previous point, which is 0.6 0.3077 because our t value is 0.6 and our y is 0.3077, and we just find the slope of that. We only plug in our t, which is 0.6, because our derivative function was only using the t value, so 0.6 pi. So we plug in our slope, which is sine 0.6 pi times our delta t, which is 0.2. We just do the same thing on the calculator. I'm going to hit plus so I don't lose that number. Plus sine 0.6 pi. Make sure to use your parentheses. Times 0.2, which equals 0.497 ... 497 blah blah blah. One last step and we'll have our answer. So our next and final step will be y of 1, because 0.8 up 0.2 is y of 1. Approximates to the y value of the first point, which is 0.8497. So our y value is this one, so 0.497 ... plus the slope of this point. So we go back on the side and do that. And once again, we're only using the t value, which is 0.8, and we're plugging that into our derivative function, which is sine pi t, so sine 0.8 pi. So we plug in our slope, multiply that by our delta t, which is 0.2, and we plug it into the calculator one last time. So hit plus and add your remaining values. Times 0.2 equals 0.615. So now here we can round. So I will round to a 0.62, or you could do 0.615 if you want, or 0.616. So there's your answer. So it turns out to be a 0.62 or 0.616, however you want to round it. So yeah, that's how you find and approximate a value using a given number of steps. You just find your interval and go on through using Euler's method from there. So that's how you do that. And thanks for watching. Comment, like, subscribe, and yeah, hope you learned a lot.